Hello out there in virus land. Today we're going to talk about the integral test. And the integral test is one of the best ways to wrap your head around this idea about convergence. And so that's the important thing that we have to get at. Keep in mind that when we talk about series, we're not interested in series for themselves necessarily, but as a stepping stone toward looking at power series and other more general kinds of series. So this is a tool that gets used in something else. It's kind of like graphing, which we're going to use to do something else today. So a lot of times we have tools that we develop to work on the real problem. And the real problem here is, how do we understand convergence? Let me remind you about improper integrals. So the situation that you have here is some function y equals f of x, and you want to do the integral, let's say from 1 to infinity, the left endpoint doesn't matter so much, of f of x dx. Now, this is clearly ridiculous, although people don't seem to object to this as much as they do to the idea of an infinite sum, and partly because this can be a little bit easier to work with. So let me remind you how we do this. And what we do is we cut the whole thing off. We say the integral from 1 to infinity, can't do that. What we're going to do is do the integral from 1 to t for some finite t, and then take the limit as t goes to infinity. By the way, everything we're talking about here today is positive functions, positive terms to the series. So what we're going to do then is do this integral test, and so we have the limit t goes to infinity, integral from 1 to t of f of x dx. So that's how we handle it, and we found a whole bunch of things really do converge this way, and you can actually calculate what the area is. We're not going to be able to do that with series. We're just going to be able to get an estimate. We're only going to be able to tell whether the series converges or diverges. So let me remind you of something else that no one ever seems to question very much. That includes me, which is the Archimedes limit. That's what makes this all go, is limit x goes to infinity of 1 over x. That's 0. Everybody believes that, so we're going to use that as well. Okay, so we're going to take a series that we have a formula for the terms, and so let's just say we'll just use f again. A sub n, the nth term, is f of n. That's not that hard to wrap your head around. So like if you have a sub n is 1 over n squared, then f of x is 1 over x squared. And so, yeah, we're just looking at this at the whole number inputs, not arbitrary inputs. So we're generalizing a little bit, but that'll be okay. And we know, by the way, that the integral of f of x converges by the p-test. Okay, so what we can do is look at the integral this way. We're going to take the graph of y equals f of x, and we're going to look at the integral and relate that to the sum. So what we're going to do is subdivide. That's how we always do integrals. Subdivide, sample, sum, and sometimes take the limit, this being one of those times. So there's our subdivision at whole number points. And let's just start being optimistic. Let me show you a very crude estimate, so I guess I'll do this in red. There's some rectangles that estimate the integral. They're clearly less than the value of the integral. But if you look at what's happening here, this one, the height is a sub 2 and the base is 1. Then the height is a sub 3 and the base is 1. And then the height is a sub 4 and the base is 1. So the areas are a2, a3, a4. We're skipping a1, but one term doesn't make a difference with convergence. It changes the sum, but not the fact that there is a sum. So what we're seeing by this picture is that if we start adding at A2, what we get is less than the integral from 1 to infinity of f of n dn. I guess I've changed numbers on you there. So what that means is if this integral converges, if that limit exists, this limit up here, which is how we would do this integral. If the limit exists, then the sum is finite and everything is hunky-dory, yay. The alternative is to look at this estimate for the integral, and so this will be the green estimate, and we're going to see something slightly different, which is, let me finish the picture. So the green rectangles have areas A1, A2, A3, so forth and so on, and the sum of the areas of those rectangles is clearly bigger than the integral. So that one, by the way, starts at A1. So what we have is in green, A1 plus A2 plus A3 plus A4 plus blah, blah, blah is bigger than integral from 1 to infinity of f of x dx. So there we go. Remember, I'll put this up on the Moodle page so you can look at it at more leisure. So the red interval, subdivision and so forth gives you an underestimate. The green one gives you an overestimate. And so where the conclusion is important is that smaller than convergent is convergent. Bigger than divergent is divergent. So if the integral diverges, then the sum is bigger. It's bigger than a divergent integral. And so that means the sum diverges, that the limit of the partial sums here is infinity. And here, if the integral converges, then that means the sum is less. So if this has a finite limit, then the sum has a finite limit. We don't know what it is because there's an awful lot of error in these estimates, especially at the beginning. We don't know what the sum is, but we know there is a sum. So the integral test says what you do is you go back to this situation, a sub n is f sub n, and you integrate f sub n, that's an improper integral, and if it converges, the series converges. If it diverges, then the series diverges. And so that is the integral test. So I will just write that down. Integral 1 to infinity, f of x dx converges. Now remember, we can do what the integral was. We can do the integral exactly. We can't do the sum exactly this way. We cannot do the sum exactly this way. You can get some crude estimates. That sometimes is good enough. Anyway, that means that the sum, n equals 1 to infinity, of a sub n converges. And this works both ways. So that's the integral test. That's how we can think about convergence in a way that's more natural and move on to do different things. So put on your bandanas and stay inside and stay healthy and keep doing some math.